Raffaele Tito d'Angolo, again on microwave cavities.
Yeah, thank you very much for the invitation. Can you see my slides and hear me well?
Yes.
Yes.
Okay, perfect. So yes, so I will also talk about detecting gravitational waves in superconducting radio frequency cavities. And actually, this talk is a continuation of Diego's talk. We are in the same collaboration. I will focus more on the heterodyne part of the idea and on the backgrounds, and I will give you at the end a preliminary sensitivity plot for detection in the kilohertz to 100 megahertz range. So slightly different compared to what Diego just showed you. Since he already did all the theory work, I will pretend, I think not very successfully, to be an experimentalist, and I will give you a bit more details on noise and cavity design, etc., but not that much more. Okay, so why did we start thinking about superconducting microwave cavities? Well, the reason is that it's kind of a classic idea to look for gravitational waves using electromagnetic fields when you're looking at high frequencies, as we are at this workshop. But the precision with which we can measure electromagnetic fields is not really comparable to the one of LIGO, so to the precision with which we can measure distances. So it's almost impossible to just have a brute force measurement of a magnetic field induced by a gravitational wave. And to some extent, we are forced to resonate. And these SRF cavities are essentially the best electromagnetic resonator that I know. They reach quality factors that are close to 10 to the 12. And to some extent, with some creativity, you can even tune them so that you can scan different frequencies of the gravitational wave, as I will show you in the following. And the magnetic field that they support, so the one that you can use to generate your signal, is relatively large. I mean, it's not the largest that you can have in a laboratory, but it's still of the order of 0.2, 0.1 Tesla before you destroy the superconductor. Okay, so I will go quickly in the description of the idea because you've seen it already from Diego to a large extent, but I still wanted to make the talk self-contained because I know that you're recording, etc. So the aspect of the story that I will mostly focus on is the heterodyne detection of gravity waves. So we are going to imagine to build a cavity in such a way that there are two modes, this one at omega 0 and this one at omega 1, that are relatively close to each other in frequency. So their splitting is smaller than the typical splitting with the other modes. And we put electromagnetic energy in this mode at frequency omega 0, and then a gravitational wave hitting the cavity can move some of this energy into the other mode at a higher frequency. This idea is not new. It was proposed in the 80s by several different groups. We realized recently that you can use a similar setup to look for axioms with potentially very good results. And what I'm going to talk about today, and Diego's already partially talked about, is to revisit these ideas for gravitational waves. And what I mean by revisiting, well, on the one hand, there is a technological aspect because, well, these kind of cavities are not the same that they were in the 80s and not even the same that they were in 2005 when the last prototype for this kind of experiments was made. Secondly, in the original calculations from these papers that I mentioned in the previous slide, it was missing the calculation of the direct coupling between the gravity wave and the electromagnetic field. So the signal that they were looking for was the cavity being deformed by the gravity wave. And finally, since these ideas were initially thought for low frequencies, only the leading order metric was used. And as Diego said, we tried to generalize also to frequencies of the order of the size of the cavity. Okay, so just to briefly recap what kind of signal you can expect. Well, first of all, you can deform the cavity if a gravity wave is arriving. And if you do that, well, my particle physicist way of thinking of what's going on is that the graviton is converting into a vibrational mode of the cavity, so into a phonon. And there is this photon, phonon, photon vertex. And so if you have some electromagnetic energy, say at frequency omega n in the cavity, you can generate some electromagnetic frequency at a higher frequency through this process. The second possible signal that you can have instead is straight up a wave arriving and converting some background electromagnetic field into another electromagnetic field, possibly at a different frequency. And my jargon for the talk will be calling electromagnetic the signal from the left-hand side of the slide, and mechanical the one from vibrations on the right-hand side. If you roughly estimate what you expect for this signal, well, you're gonna get that if your background electromagnetic field is oscillating, you have, well, in front, all the factors that you expect. So some dimensionless amplitude of the wave, some background magnetic field, and then if you're resonating a square root of the quality factor. And then there is some suppression if you're looking at gravitational wave frequencies that are smaller than the typical resonant frequency of the cavity, just because the physical effect is coming from the Riemann tensor, as Diego showed. So there are two derivatives of the gravity wave involved in this process. If you instead have a static magnetic field in the background, so what Diego described as ADMX style, the suppression is even more. So there is an extra power of frequency of the wave over frequency of the cavity. And the reason is that what's exciting your resonator is a time derivative of the current. So you have to take another time derivative of the wave times the field. And if the field is not oscillating, you're paying an extra price. So this is why we're initially focusing on this heterodyne setup. And then, okay, as a byproduct, we're also showing the other sensitivity. In principle, it's not obvious just from this simple parametric argument which one is going to win, because of course you can turn on a much bigger static magnetic field around a normal conducting cavity than you can turn on an oscillating magnetic field inside a superconducting cavity. But we find that typically the oscillating option wins at frequencies of the wave that are smaller than the typical size of the cavity. Finally, so the mechanical signal doesn't really have the suppression that I just described, because the wave is really exciting a resonance in the cavity that is at the same frequency as the wave. So these mechanical resonances are not at the same frequency as the electromagnetic resonances of the cavity. They can be also at lower frequencies. So you do not necessarily need to pay this price. And this is why originally people focused on this signal. We found interesting to think about also the other signal because it's different from typical backgrounds, right? So the cavity wall vibrating is something that your environment can do for you. Instead, if you have some, say, active feedback mechanism that dumps these vibrations, you can still have this other electromagnetic signal that I showed you, sorry, in the previous slide, but you might set to 0 this signal. So even if parametrically you expect it to be bigger, it's not necessarily, at least a priori, the only way to go. Okay, so this was to summarize the general idea, the parametrics, but you'd already seen most of it in Diego's talk. And now I want to convince you that we've done at least our theory homework as far as the backgrounds go. Then, of course, there will be more to do experimentally once the first prototypes come online. So as I mentioned at the beginning, this kind of idea was already proposed in the 80s, and the original collaborations went all the way to building a prototype in 2005 called MAGO. It's the cavity at the bottom of my slide. And this was very useful for us because they already made essentially 99% of the noise measurements that we needed. And we can just use their numbers to estimate our backgrounds. And as you can see, I mean, this is technology from more than 15 years ago, so our estimates are going to be conservative. Okay, so this heterodyne idea that I described compared to, say, a case with a static magnetic field that you might be more familiar with, has, of course, many more sources of noise that you have to consider. because you're already putting oscillating electromagnetic frequency in the cavity at a frequency not that far from the one that you want to read out as your signal. So you don't have only thermal noise mimicking a signal, but a bunch of other effects. And I will focus on two that are most important, and I will be happy to take questions on the others if you are so inclined. So I will start with the most obvious one, which is the fact that when you put electromagnetic energy in the cavity, you do it with an oscillator that is not monochromatic. So it's going to have some spectrum, and some of it can leak to the signal mode that you want to read out. This is the form of the power spectral density for this source of noise. So if you integrate this in frequency, you're going to get the power in this noise source. The last term in the expression is just a normalization, so you can ignore it. We found useful to normalize the noise to the total power that you're putting in the cavity. Then there is this response of the cavity, which essentially is what you get from an harmonic oscillator. It's just a bright Wigner, so nothing surprising here. Finally, there is this epsilon factor that is probably the important one experimentally, which is essentially telling you very roughly, theory level speaking, how well you measure angles inside your cavity, because you're going to design your setup in such a way that the directions of the electric fields for the loaded mode and the ones for the signal mode are different in such a way that you can distinguish them geometrically. And I can be more precise if you want to know how exactly. But the important take-home message is that the Mago collaboration had already proposed a readout design that can reduce this overlap, this geometric overlap between the modes to a level of 10 to the -7. So, and this is what we're going to use as a benchmark in our noise estimates. Finally, the last ingredient you need is the spectrum in frequency of your oscillator. And this we took from something commercially available. So we just called the company and got this nice picture here. Vibrations are also important. So they are the closest to one of the signals that we're looking for. And let's say analytically, they're very similar to the source of noise that I just described. So there is a factor that comes from the response of the cavity. In this case, you have two bright Wigners, one from the electromagnetic modes and one from the mechanical modes, but nothing surprising. You still have this epsilon factor because vibrations are not flipping the direction of the electric field. And so only electromagnetic energy that's already leaked in the right polarization, let's say, can contribute in this case. And again, we took the same number from the Mago collaboration. And finally, you have the spectrum of these vibrations. And this was also measured by Mago in the frequency range that we care about. But we complemented with this information with the attenuation of vibration that dark SRF was able to achieve a couple of years ago. So essentially, we're taking the shape from Mago, which includes ambient noise, including from the cooling system, et cetera, and we're taking the normalization from what dark SRF could do. Finally, there is one effect that we're still working on, but we think is not going to affect us strongly in the frequency range that I will show you in the end, which are cavity nonlinearities. So another effect that one has to take into account is the fact that, well, the cavity is not a perfect harmonic oscillator, both due to impurities in the walls and to the fact that also the superconductor is not responding as a perfect harmonic oscillator. Theoretically, we found that we can describe impurities with an effective Josephson junction model, and we can describe these intrinsic nonlinearities in the superconductor with an effective Landau-Ginzburg model. So this is kind of the quantum field theory part of the work. This is exactly like the Higgs Mexican act potential. It's the same theory. And so we will try to get some theoretical understanding solving these models numerically. But most importantly, we are starting to make some measures. So there is some measurements at CERN that are supposed to take place probably in January or February, and some others already ongoing at Fermilab, but from which we are hearing only rumors. But from the rumors we've heard, this effect should be negligible for us. So what I'm going to show you in the following does not include it for the moment. But okay, you should stay tuned for updates. All right, so putting these stories all together, here I'm showing you the power spectral densities of these noise sources for two sets of experimental parameters. So on the left-hand side, we have the geometric rejection achieved by MAGO 15 years ago, and a quality factor that is a bit futuristic, let's say. And on the right-hand side, we have the same quality factor as MAGO and an epsilon that is 100 times worse. So this is, the right-hand side is worse than what was achieved 15 years ago. I apologize, these plots were made for the axion, so you should not look at the bottom axis, but you should look at the top axis where you see frequency. And well, if you look at both plots, you're gonna see that up to roughly a megahertz, thermal noise is always the dominant source. So we did all this work, but in the end, we could have even avoided it. This mechanical power and this phase power are the two sources that I described in more detail. So phase refers to the noise from the oscillator and mechanical from vibrations. And you can see that, well, in the case that's worse than 15 years ago, after a megahertz, you need to take them into account. But in the case that is closer to what we can do today, even if with a larger quality factor, but it's not going to change a lot if you decrease it to a few times 10 to the 11. Essentially, we can, thermal noise is dominating all the way down to a kilohertz, whereas where roughly we're going to stop looking for gravitational waves for reasons related to the signal becoming too weak for us. And so the take-home message from this whole part of the talk is just that our dominant source, we expect our dominant source of noise to be thermal in this frequency range, which is the one that we're gonna explore. And now I'm gonna show you some sensitivity of this heterodyne setup, which, however, is very preliminary. So you shouldn't hold it against me if it changes a little bit before we publish the paper. However, it's going to give you an idea of what this setup can do. So in red, I'm showing you the signal only from the electromagnetic coupling. So a graviton coming in an electromagnetic background and generating another electromagnetic field. And in blue, I'm showing you what you can do with mechanical resonances. You should ignore the mechanical part below a megahertz. It's going to get a bit worse. And I can explain to you why if you're interested in. But again, so the main point of this plot is that there is some interesting sensitivity, mostly above a megahertz, which is close to this benchmark from primordial black holes that we took from the previous review in the workshop. But okay, the strain sensitivity is not spectacular and is probably not going to get all the way down to interesting cosmological sources. The way these lines were made was, so in the solid lines in the mechanical case, we assume to be able to tune the two modes at each point so that they're split by the frequency of the wave. And this can, for example, be achieved with some piezoelectric sensor pressing on the wall of the cavity, but the detailed design is still under study. The difference between the solid and the dashed line is that on the dashed line, we've assumed that there is a mechanical resonance also at every point, which is actually close to what MAGO was finding. So there are mechanical resonances separated by, I think, order 100 Hertz. So they're pretty dense. So the final sensitivity is going to be in between these two lines. So for certain points, you're going to have resonances that go all the way to the dashed ones. And for other points, you're going to be on the solid one. Yes, so this concludes what I wanted to tell you today. It would be interesting to go beyond 100 megahertz. Here we didn't do it because we wanted to be in the theoretically controlled regime where there were two modes that are close to each other and all the rest are separated, but it might be interesting also to explore more complicated setup with a forest of modes. And as you can see, there is not much point going very much below a kilohertz, mostly because the sensitivity starts rapidly getting worse. Maybe for the mechanical case, it's worth checking what's going on, and we will. But if you want a rough idea of what this idea can do, you'll see it in this plot. So frequencies between a kilohertz, maybe you can go a factor of 10 up here, and strains of this order that you see on the y-axis. Okay, so to conclude, I'll just spend 2 minutes on what's the status of the collaboration, let's say. So as I mentioned at the beginning, we have a proposal for axion detection, which is more advanced. So the theory papers are already out, and we found money to build a prototype. So in principle, in the next 2 years to 3 years, we should be able to build and test this prototype, which has already some good sensitivity to axion dark matter. So you can see the blue line here for different choices of parameters. The nominal ones given by the line in the middle of the band are here on the right-hand side, in case you're interested. And well, what's interesting for this gravity wave story is that all the noise sources that I described, including the ones that we're still working on, will be tested directly on this prototype. Also, the scanning mechanism will be tested on this prototype. So all the relevant technology will be there, except that the geometry of the cavity will be different because, as Diego said, the axion couples to E dot B, while the gravity wave couples to E squared plus B squared. So you need to choose different modes. But the bulk of the work experimentally to make this idea completely on shell will be already done for the axion. Okay, so to conclude, we did our theory homework so far, both on the signal, as Diego just explained, and on the backgrounds. We hope to see results experimentally already in the next 2, maybe 3 years. It's not yet clear. There is some sensitivity to high frequency gravitational waves. It's not spectacular, but I would say it's comparable to some of the proposals I've seen in this workshop, and I think it's interesting. There are many related ideas that I've also seen in this workshop that I found very interesting, where essentially all more or less after similar effects. And we expect to put out our paper maybe in the next month or so on the theory part of this story. So it will contain mostly what Diego said. And we don't have yet an experimental collaboration formed or money or any formal organization for the gravity wave part of this idea. So if you're interested, let us know. Thanks.
Okay, thank you very much, Raffaele, for the nice talk. Are there questions? Michael?
Yes, this parameter, epsilon, is it?
Yes.
It's, isn't the MAGO detector quite different to the one you're designing, because you have 2 modes in the same volume? And to me, that looks like, isn't the cavity you're building a little bit different to the MAGO detector? Because that seems to have two modes, where yours has 2 resonances in the same volume.
So for the axion, it's true, but for the gravity wave, we're not committing to a design yet. So we are coupling to the same modes as the MAGO people. So in principle, we could also imagine to have the same detector.
Yeah, because that's if they're in the same cavity, it restricts your ability to get a small difference frequency.
So you mean for the readout, or for just finding
for the readout? Yeah. So and for the mode as well, because what sort of power are you going to put in the cavity for your signal mode?
Yes, so the power that we want to put in is of order of, well, the energy is of order this for the prototype that I just showed you.
Yeah. Because with such high Qs and such high power, you're likely to excite the mode if it's close, a four-wave mixing process or something.
Yeah, so this is what I was talking about in terms of non-linearities. So we've already done some preliminary tests, and it seems fine. Indeed, so as you were saying, Mago has this kind of setups with roughly two cavities glued together with something in the middle. And in principle, for the gravity wave detector, we can do the exact same thing. So for them, the loaded mode at the electric field that was, say, parallel in the two cavities, and the signal mode anti-parallel. So they were just loading by sending the same signal on both sides and reading out by summing them out of phase by 180 degrees. And this is how they achieve their epsilon. So I think that there is no obstacle in doing the same for gravity waves for us. For the action, it would have to be a bit different indeed. And the experimentalists we talk about have plenty of different ideas. So both separating spatially the two modes to some extent in some way that they have a tail on one has a tail on one side and the other one has another tail on the other, and they meet in the middle of the cavity. Plus matching inductances to the different directions of the B fields of the two modes. And we think we can do comparably to Mago.
Yeah, so when you have a coupling aboard a unity, which you usually want in these type of experiments, it then can become a further problem because they create ways for the modes to couple together. We've got some experimental results which look at this.
Yeah. So we are aware, and as I said, okay, the preliminary measurements that were made seem to signal that everything is okay, and I will be able to tell you more with the prototype when we fix exactly what two modes we want to look at, etc., etc. But a priori, we think it's going to be fine, that we're going to be able to couple predominantly to one mode with the input and read out predominantly the other mode.
Okay, no problem.
Okay, Subodh, have you a question?
Yeah, so I was just wondering if you could maybe elaborate a bit more on maybe the cooling mechanism or how you sort of control thermal gradients in this setup, because just like for an average metal, typical metal, your stress coefficient is about 10 to the minus 6 per meter Kelvin, and it seems like you need to have this control of this epsilon parameter to like an order of magnitude less than that. So so I was wondering if you could if you have any information about that.
Yeah, so this number that I gave you was already, that's what they'd already done in this cavity, that they were cooling at 2 Kelvin. So they put the cavity inside the refrigerator, they had a tuning mechanism from outside. So maybe this is the point that I should make more clear. So it's not that epsilon is 10 to the minus 7 straight up from the beginning. So they were putting the cavity in the refrigerator, loading it, and then tuning these magic T's that I showed you in the backup to get this 10 to the minus 7. So I don't know if this fully answers your concern. As I said at the beginning, in this talk, I was only pretending to be an experimentalist, so this would be better addressed by my collaborators. But what I can tell you is that this number that I showed you was already demonstrated for the same temperatures that we're thinking about.
Okay. Okay, then maybe I could just ask a clarifying question you could explain to me. So is this epsilon got to do with the geometry, like how well you understand the geometry of your detector, and that if it deviates from more, well, it's got to do with the response electric field to something happening inside, but is it right of me to think that if your detector is sort of deformed anisotropically by more than that amount, then that changes that number? Is that a fair understanding, or did I misinterpret that number?
Well, yeah. So maybe my cartoon explanation was more confusing than anything. What epsilon literally is imagine that you're putting power in the cavity as this cartoon on the left-hand side. Okay, so you essentially load the cavity with two electric fields pointing upwards on both sides. And then you read out the cavity at the same frequency, but now you sum these two guys by flipping one by 180 degrees, right? And so this epsilon is the suppression between the two amplitudes. So if you have some power in this configuration, the power out that you get is 10 to the minus 14 at the same frequency. And this is what we care about for our noise. And this is what was achieved. What you're describing, the amount by which you can deform the cavity, it re-enters in the noise through the vibrations, and roughly it's going to be of the order of the same parameter, but indeed it's a slightly different physical effect.
Thank you.
No problem.
Sebastian?
Yes, a quick question. In the plot that you showed with the strain sensitivity, which design did you assume for the electromagnetic coupling curve?
Which design, in what sense? So you mean
for the detector, because the line seems to be in the, well, not the same frequency dependence than in the talk by Diego just before. So, in W, and here it decreases with W.
Yes. So what Diego was showing, I think, was we're showing the same stuff. The only difference is that in my plot, I'm showing the heterodyne case, so where there are two modes split by the frequency of the gravitational waves, and you put energy in the lower mode. And Diego was showing the case where the background magnetic field is static instead.
Okay.
So indeed, the frequency dependence is not the same, but in both cases, the derivative is the same.
Okay, great, thank you.
No problem.
I have just a question. Can dynamical Casimir effect play a role in the noise?
In the noise, yeah. So I think, yes, it's, I kind of bunched it together with the nonlinearities. So what we're gonna do is we're gonna try to just treat it phenomenologically from the theory point of view. And from the experimental point of view, we're just gonna straight up do a measurement similar to what I described before. So we're gonna put power in one mode and read out the other modes and see what's coming out.
Okay, I see. Thank you.
No problem.
Another question by Axel.
Just want to come back to the side question asked in the conclusion slides. Mm-hmm. So I've briefly touched on this in my presentation, that DESE is also building what we call a cryo platform in the Hera North area, which should be operational 26, 27 or so. I hope still for 26. So this is the old Hera North Hall, so quite some space. And what we provide there is also 4K helium, just for anyone who would like to have significant consumption of helium to cool down, for example, cavities. So I cannot promise anything, but maybe you can send me an email just sketching your requirements on a site, that we can at least start discussing this at DESE.
Yeah, that would be great. I can already roughly tell you that, okay, for the prototypes, we're thinking tens of centimeters in all directions. And for the final thing, maybe a meter, so a meter cube, which might be challenging, but I don't know. I mean, maybe your fridge is going to be big enough.
Okay, thanks.
Other questions? Okay. Well, thanks again to the speakers, and I think that we can close the session.
Yes, so many thanks to Francesco for sharing this session. Let me stop the record. We will reconvene at 10 past, so in half an hour. But let me say that